For the first talk after lunch, we needed a talk that was full of energy and vibrancy. So I am stoked to introduce Stuart and Alden, who will be walking us through a DPRK Intrusion. Round of applause.
How's it going, everyone? Hopefully lunch was exciting and lovely. I don't know. So yeah, welcome to our talk, BlueNoroff's Clues. We're going to talk through some DPRK intrusions we saw this year, and yeah. So I'm Alden. I'm an Intel analyst at Huntress, and I'm speaking with Stuart.
And I work at Huntress as well as a macOS product researcher.
So a quick agenda. We're going to do like a quick background on BlueNoroff, like why they're different than just like all the other DPRK groups. Then we're going to do some technical analysis of some malware that we observed in this particularly cool intrusion. We're going to then go to detection opportunities, see how you can find more of this malware, and then close it out with some like new stuff that we've observed like very recently. So BlueNoroff also tracks as TI444. They're like my goats of macOS malware. Like they are like one of the better tiers of like DPRK APT subgroups. They're again like a financially motivated actor, so their whole shtick is they like go after crypto companies, whether they're like big exchanges or just like people who have lots of money, and they steal that to fund the regime. I think like every malware person in this room's probably got a blog out of them at some point. So like they're great for everyone except crypto folks. But in terms of like their targeting and like their tooling, they're really good at writing macOS malware, even compared to like other DPRK groups. So yeah, with that in mind, let's jump into the analysis.
Cool. So before we get started on the in-depth analysis, we want to give you a brief overview of everything we're going to talk about because there's a decent amount here. So we're going to start with initial access and how this got on the victim's machine, move into how it persisted, talk about a backdoor that was involved with it as well, and then some really interesting things. So a keylogger, everyone's favorite info stealer, which we'll talk about very briefly, and then a dropper that did some very unique things with process injection on macOS.
So while we were REing all these samples, we started to notice there was a lot of like build artifacts. So a lot of these are written in like Go or Swift or like other like modern-ish languages that tend to leave a lot of like build artifacts from your host / like whatever other associated build data. So like if you're compiling Rust, it'll do like your users / your username / your cargo config or whatever. And those will get stuck into the binaries. And like most of the binaries in this chain had that. And so we were able to reassemble like a sort of, like these are all like the usernames that we saw. And it's kind of neat to put like a face, I guess, to the people who are like behind some of these operations. So we were able to sort of like see that like Dominic obviously carried the class here. He wrote most of the stuff and most of the cool stuff, and everyone else was kind of just like tagging along. So yeah, fun thing to keep in mind when we're talking about these samples.
So first we'll dive into initial access and the Apple script dropper. So in this case, the victim in this situation worked at a crypto startup, as expected, being a BlueNoroff intrusion. They received a Telegram message about setting up a meeting to discuss some investment opportunities, and the threat actor sent them an invite via just a regular calendar event, which you can see here. It originated as a Google Meet meeting. Not long before the actual meeting, they did change it to Zoom, which could be a red flag there. And when the victim got on the meeting, they couldn't be heard from the other people in the room. And so they were told that they need to download a SDK from Zoom or a plugin in order to make it work. So what happened was they opened up this file, and it was a malicious Apple script. So in this case, what it would do is it would actually open a legitimate Zoom link that went to their actual SDK page. But in the background, and in this script, after about 10,000 blank lines of nothing, they had a few lines where it would actually curl down a second stage from the malicious domain. So that script had more lines of code, was shorter though, and could do a few unique things and a few unique checks. So it would silently install Rosetta if it wasn't, so x86 payloads could run. It would then create a file in the user's shared directory called .pwd. It would download the payload from the fake Zoom page to a file called iCloud helper in temp, and then it would also remove the shell history. It's also worth noting that it used a cur1 request user agent, which Kaspersky has attributed to BlueNoroff back in 2022. So a good indicator if you see that BlueNoroff is involved.
Yeah, and it's seen all the time in like a bunch of macOS chains. So I also just thought it would be fun to include what this actually looks like if you are a victim receiving stuff like this. So if you go on Twitter and you search like DPRK tried to hack me or like crypto hacked, whatever, there's a lot of like crypto influencers, like yuck, but like that are talking about them getting targeted by this particular group. And so the video on the left is like a screenshot of essentially a recording of a prominent person in the crypto space. And then they include like this little snippet that says your Zoom SDK is out of date, like install our stuff. And so they send that in the chat, but it's in the video, so it looks like a pop-up. Yeah, and then like obviously people respond, they're like, I didn't do that, don't get mad at me. So yeah, hopefully that just keeps you understand what like victims are sort of seeing. They also tell you how to run their malware. So they ship a little video that's like, here's how you can download and run our Apple script in the script editor. So yeah, after that, the first actual like binary that gets dropped is called Telegram 2. It's very simple, and it's mostly just to set up the stage for the rest of the infection chain. So it's the persistent part, and it will start off like running every hour, and it mostly just keeps configuration info. So it stores like some keys, like a client key and a server key, that is used later on by different implants to like establish secure comms between the C2 and the implant. Yeah, and it persists in like user application support Telegram 2. It was ad hoc signed, and I think the ad hoc signature was like root startup loader ARM64. So I wonder what that is. The only thing it does is write a config file in like private var temp config, and it will put some like key information in there so it can be accessed more easily later.
So now we'll talk about the backdoor, also called remote D. According to the build artifacts, Dominic's build artifacts, they also called it root Troy v4, hence the RTV, but we'll kind of use those interchangeably. I'll mostly stick to like backdoor and remote D. So this is where we are in this attack chain here. So this backdoor ran out of library web server bin, and it was written in Go, and its primary function was to execute AppleScript. So the way it would do this is it would create two threads, one to start executing the AppleScript, the other one to basically check and see if the user has logged out, and if they have logged out, rerun this AppleScript. So what they would do is they would download the payload, write the response out to syscon.zip, and then extract those contents with a password that's called gift123, and we'll talk more about that in a bit. But essentially, they would go through here, try, and if it failed, go ahead and continue. And eventually, they would drop this binary called A, which was the loader that did the unique process injection. However, that wasn't all that this backdoor did. Whenever the user logged in, it would initiate the info stealer, which is ARMOND, as well as the keylogger out of this script called .startup. And that .startup file lived in a different directory in library Google cache. And it sat there along with two other files. So one is a hidden config file .cfg. That was encrypted with an RC4 key and contained just C2 information along with user IDs, which we went ahead and redacted, the startup script file, and then a version file. And this tracked just the versioning for the, in this case, CBOT, which stands for CryptoBot, which is their info stealer, and then RT for root Troy, this backdoor. Some other unique functionality about this backdoor is its ability to achieve remote code execution. So it had three ways of doing that via three different functions. One called exec script, where it was essentially a wrapper for running OSA script. Exec shell, which would basically synchronously run a shell command. So think hands-on keyboard. And then one that could run in the background or asynchronously via exec shell detached. Lastly, Via the check sleep function, it would run system profiler and more specifically SP displays data type and check to see if the display was actually online or not. And if it wasn't asleep, it would go ahead and put those commands into a queue to be executed later. Some small additional functionality, basically after this more unique stuff, it would also go through and collect the data from the volumes directory, as well as any running process, and ship those off to the C2 in like this infinite loop. So with that in mind, let's talk about, in my opinion, what's one of the more interesting parts about this intrusion, which is the loader called A.
So yeah, this was like the binary that got all of us excited. Like we were like, okay, fine. Then we got to this and we got all giddy. If you're like a Windows person, which I don't think there's probably many here, but like you hear process injection and you're like, we've done that for 20 years, like whatever. But in the macOS space, like I haven't seen it before, and there's like loading from memory, but this is sort of different and it's a little more creative. So this inject with dilid binary, or this like A, has two base64 and encrypted macOS embedded within it. And so there's one called base app, which is like a benign script that, or Swift binary that just runs random numbers forever. And then there's a NIM Trojan. So they use password-based key derivation using that gift password from earlier to derive like an AES key, and then assault, which was just prepended to the base64 actual like Mako payloads. So using that key, they decrypt both the base app and the NIM Trojan, but they only write the benign app to disk. And that's because they are going to end up injecting that malicious payload into the benign app on disk. But in order to do this, they need specific entitlements, specifically like the debugger entitlement. This allows you as a process to start interacting with other processes as if a debugger would. In this case, since it was ad hoc signed, both of the binaries involved were signed with this, to like one to allow receiving debugging and then one to allow debugging. Specifically, this is important for the task for PID API call, which allows you to get mock port so you can start accessing memory of other processes. So the way that this actually occurs, like in the binary, is that they first spawn the benign binary in a sleeping state. So they create a new thread, it's sleeping. Then they get a mock port for that sleeping binary. And then they list out the task threads for the process. There's only one, and it's the sleeping one. So then using that thread, they're able to start mapping the malicious executable into the memory of that process. So what they start doing is they iterate over the Mako header of the NIM implant, going segment by segment and figuring out how much space they need for each segment of that NIM binary in the form process. So after they figure out the size by subtracting the base address from like the section size or segment size, they allocate that much memory, and then they will write that into the suspended CloudKit process. So they'll map it into memory. First, they change the protections of the memory, then write the payload, and then convert it back to how it was protected before. After that, they will then resume the thread and then continue execution. And then instead of the suspended CloudKit binary, you get a scary NIM implant. The NIM implant, though, is actually like kind of uninteresting. Of all of the like cool things to protect, I wouldn't think it was this one. But essentially, it just sets up a WebSocket connection to the C2 server, and then allows for like standard comms via just like JSON blobs. So there were certain message types. Some of them were like collecting system info. Some were like for command execution, and these were basically just like sent back and forth over WebSockets. They were encrypted using a bunch of different keys. I think there was like 5 in this binary. But yeah, a little side note here, if you're reversing NIM, there's no support for it in any of the tools. And the strings are kind of like Go. There's basically like a structure that has like a length and then like a delimiter and then the actual string data. So if you're reversing it, you can like start recreating these structures to like make your life a little bit easier. The stuff below is like what they look like before you've created those structures, and it's disgusting. The bottom left screenshot is sort of how they're parsing JSON. So they have like these weird, like gross string routines, and disgusting. Yeah.
All right, so now we're going to talk about the keylogger, which isn't anything too novel to macOS, but this one had some interesting traits that we're going to talk about. So in addition to keylogging, this keyboard D binary also could do screen capture, recording, and retrieving contents from the clipboard. So how it did this, and it's worth noting this was the only part that was written in Objective-C. So this was called repeatedly by that remote D backdoor with the P flag to monitor the clipboard. And it uses the core graphics library, more specifically this event tap create API. And so this API takes a callback function that will execute anytime a key press event is registered. And so what it has to do in order to track which key press belongs to which application is grab the foremost application, and they do that by grabbing the app name's bundle identifier, the bundle ID of the app. So if it's the same, they go ahead and log the time and the name out to the keylog buffer, but if it's different, they will log that new foremost application. Finally, they check if the key codes that are pressed are actually printable, and if it's a special one, such as control or command or all these ones on the right and additional ones as well, they go ahead and convert that to a text representation before they append it to the buffer.
Woo, info stealers, everyone's favorite thing. So yeah, the info stealer in this case was not super special. It was very specifically targeted towards crypto stuff. As with other binaries we looked at in this chain, there's a lot of like associated helper files that they were sort of using to keep data in. There's airmond, which is the actual like info stealer binary. There was a cache folder, which is like when they would steal data from these crypto extensions, they would write it to this folder. There was also a CF user text encoding file, which contained like the username of the host and then RC4 key. And that key was used later on to make sure that the like other cache files and whatever was encrypted on disk. So yeah, it was just AES encrypted IV of 0, because like, why use good crypto? And again, like this isn't a super special stealer. It did get a lot of wallets, which was like neat. But the thing that they did do, which I sort of respected, was that for each of these wallets, they wrote a custom parser to verify that the results they were getting from this extension were actually like useful to them and valid before they shipped them off the host. So they weren't sending themselves like a bunch of junk, because like typically stealers will just like put all this stuff into a folder, send it off, and like parse it later. But they really cared about quality over quantity, I guess. There was a bunch of helper functions for like managing the cache state, making sure that there was no like multiple instances running, stuff like that. And all the strings were RC4 encrypted with this static key. So yeah.
So that covers the whole attack chain, but we didn't want to leave you with just kind of a broad analysis. We also wanted to give you some potential detection opportunities that you can take back to your, whether it's your EDR or threat hunting or anything like that. So there's a lot here, and we'll just cover a couple that we'll also make available later. But first, you can kind of see a suspicious process called remote D spawning OSA script. So you can view this as kind of a parent-child relationship, remote D the parent, OSA script the child. You'll notice that you see OSA script is 3 of 3, and then bash is 4 of 3, and the reasoning is because bash was piped to from OSA script. So those in Jaren's training, this might sound familiar, but if you can grab the process group ID, the leader specifically, and pivot and grab the path, you can actually see if something like OSA script gets piped to bash. Generally, with endpoint security, you're a little blind to what that path is without pivoting off of that process ID. Additionally, there were plenty of artifacts that were created on this endpoint, including things like CloudKit with kind of common Apple names, dropped in library, and then, of course, curling these files down from a very suspicious domain name.
That's not suspicious.
Lastly, and Jaren actually alluded to this in his talk earlier, but one thing to always keep an eye out for is anything running out of users shared. And to add to that, especially if it is a hidden file. So if you prepend a file with a period, it makes it hidden from both finder view and like general ls commands. So a hidden binary running out of something like users shared is something you can very much key in on.
So yeah, as part of like our lovely gift bag from this talk, we're giving some Yara rules, some Sigma rules, a reimplementation of the injector script, and some other sort of testing stuff so you can play with this malware. But interestingly, Apple released a bunch of X-Protect rules to look for this sort of chain of malware. These are the rules that hit on the stuff that we happen to have in the current analysis directory, but there is a ton of other rules that didn't hit for anything. And so we've done some cursory searches on VirusTotal. Like, we don't want to burn a retro for it, but if anyone's got a good license, let me know. And yeah, we weren't able to find too much for these. So yeah, if you see any bonsai rules, they're probably this chain. I don't know how they're tracking it, but that's sort of the general vibe. So yeah, anyways, closing up, what's new? So we found this like very recently, and I definitely didn't write this like 20 minutes ago, but we essentially found another sort of payload that was delivered via the same infection method from this chain, probably. Similar like C2 domain infrastructure and whatever. And there was like again, like a dummy binary and like a malicious dilib. These were both signed and notarized. But such is life. And in this case, the part that made me like really like, oh, that's kind of cool, is they store all of the like sensitive info, so C2 domains, IP addresses, locations of payloads and stuff as an extended attribute in the like finder comment extended attribute. So they parse this from the extended attribute like of their own bundle and then write that data to like an array for later usage. In terms of like string encryption, they do another sort of clever thing. It's just an XOR decryption loop, but like the way that they derive the key is based off of the bundle name. So if you rename the binary or you move the binary or like whatever you like mess with the state that they've put it on your machine in, it won't actually decrypt any of the like further stages necessary to like run the malware. And so like it's just like a hex key or key of 9. Great stuff. But if you just chuck it into like CyberChef, you can see that there's a bunch of like commands for like running shell scripts and running OSA script and chmodding stuff. So yeah, like, not too crazy, but again, like good consideration for OPSEC, sort of good breaking up of their chains so that if you're missing components, you can't really analyze their stuff. So yeah, we'll put our stuff on GitHub shortly. We'll post it in the Discord and whatever else. But yeah, that's all we got. Thank you so much.